Hello and welcome to the presentations on the reciprocal system of theory by Dewey B. Larson, a universe of motion. This presentation is on the concepts of scalar motion, and I, Gopi Krishna, will be guiding you through this presentation. So let's begin. First, why do we bring up the concept of scalar motion? In our postulates, we have the physical universe conforms. Its primary magnitudes are absolute. In other words, we have to find out what is the significance of the quantities being absolute and how it applies to space, time and motion. Let's have a look at numbers. In the reciprocal system, space and time possess no feature other than a magnitude as a counting number. Counting numbers are 1, 2, 3, 4 and so on up till infinity. And motion is the ratio of space to time, a scalar magnitude, a real number. In other words, we are talking of scalar motion. A relation between two counting numbers can only have a scalar magnitude. Hence, scalar motion is just that, scalar. It means that the scale of measurement is changing. Scalar motion has only one relevant quantity, scale, or it's also called absolute magnitude. There are no negative quantities and no zero. Only real numbers are used for motion. Motion of the scalar type is very much similar to the motion of the expanding balloon, which we will describe in the next slide. But please keep in mind that this analogy is not accurate, as it demonstrates the effect only in space, whereas the scalar motion that we are talking about continues in space and in time. But still, let us figure out how exactly scalar motion behaves when we look at the term scalar. Firstly, the distance, which is a scalar, between A and B is 5 units, and that between B and C is 3 units. After some time, the distance between A and B is 7 units, B and C is 5 units. In other words, every point on this balloon is moving away from every other point on this balloon, and no one particular point is ever reaching closer to any particular point. This is what we call a scalar increase in the magnitudes of these distances. Let us compare it with how we measure things. That is our vector measure. What we normally do? We attach our reference frame, or we couple our reference frame consisting of the three mutually orthogonal axes to one of the points and take that as the origin and measure all other motion from that. Now if we fix that reference system at A, then we notice that B moves away from A in the direction given by the arrow. However, what happens if we choose B? Once we choose B as the basis for the conventional reference system, A appears to move away from B, and it moves away in the opposite direction than the one shown in the previous frame. Let's just describe the first balloon. Every dot perceives every other dot as moving away from it. Motion has no inherent direction, only magnitude, as we noticed. And magnitude of space per unit magnitude of time is what we call a speed. Hence, speed is a scalar motion. And the other two balloons, where we attached the conventional reference system, they measure what is called velocity. Velocity has both a magnitude and a direction. The magnitude is a property due to the scalar motion, because scalar motion possesses only the magnitude. The direction is a property of measuring it in a particular conventional reference system, and it depends only on that. Hence, this reference system cannot represent scalar motion completely. The significance of all this is that scalar motion is found to be primary. Vectorial motion, what we normally measure, is secondary. Our conventional reference system cannot represent scalar motion completely. Thank you, and please refer to the next presentation, three-dimensional motion.